In this video, we're going to take a look at something called a Riemann sum, right? And before we get into the details of a Riemann sum, I just want to remind you, and you may have been exposed to this idea at the very start of your study of calculus, but there's this concept of the area problem, right? And again, so if you've not been exposed to what it is, well, here it is. If you have, well, this is just a quick reminder. So the area problem is defined like this, and I'll do this fairly quickly. So you have the graph of a function, right? And we've seen in the study of derivatives, how the graph of a function is really important. Well, it turns out it just keeps on being important. So for the area problem, this is how it's defined. I'm going to mark off a and a b on the x-axis, which we've done many, many times. But now I'm going to do something a little bit different. I'm going to draw two line segments. The first one will start at A, and it will be a vertical line segment. So it will go all the way up, and it will stop exactly at the graph of the function. And then similarly at B, and it will stop right there. And then if you notice, by drawing those two vertical lines, I now have enclosed a certain region. And let me color that region for you. That region is now in red. And the area problem asks this question. So what is the area of the region? And we call it a region because it's bounded by some curve, well, a curve and some lines. So what is the area of the region shaded in red? Right? And that is the area problem. Every problem for us is a question, right? And we want to know how to answer that question. Now, what makes this question a little bit harder than maybe previous area questions that you've solved in the past is that, for instance, if I were to give you a rectangle and ask you to find the area, it's simply the length times the width. If I gave you either a right triangle or some other type of triangle, you had a specific formula to find that area. So for specific geometric figures, like rectangles and circles and ellipses and trapezoids and hexagons, you have specific formulas that you can apply to get the area. But if I just give you kind of a random curve, right? Something that's not linear. So, something like a cubic polynomial or a trigonometric function or some combination of those, you're not going to have a nice formula to give us this area. So what do? Does it mean that we can't answer this question? No, it just means we have to use a different set of tools in order to get that answer. So the Riemann sum is one step in the direction of those tools, right? So let's describe what a Riemann sum is. And simply, a Riemann sum allows us to approximate the area, right? So a Riemann sum, I guess the S doesn't need to be capitalized here. The R does because it's someone's name. So oh wow, my marker there is, or my pen there is acting funny. So a Riemann sum allows us to approximate this area. All right. And I'll give you the analogy back in Calc 1 or differential calculus. The analogy is this. the secant line is to the tangent line what a Riemann approximation is to the actual area, right? So you can think of a secant line kind of as an approximation to a tangent line, and then you can think of a Riemann sum or Riemann approximation as an approximation to the area, right? And so let's describe how we create or construct a Riemann sum. So I'm going to draw another graph here with my function. I'll kind of make this, kind of spread this one out a little bit more. So y equals f of x. And I'm going to start the interval a and then go to the interval b. Let me label stuff there. And what we do is, in fact, let me go back to the first one and show you two easy ways to approximate the area. And I'll do one in blue and then one in green. Suppose I take, so on this interval, and think back to when we did like the extreme value theorem, and I talked about absolute min and max of a function on a closed interval, right? So our function is continuous, the interval is closed. Here is its absolute minimum, right, between a and b. What I could do in a very, very crude way is just say I'm going to take this y value and I'm going to use it as a y value over the entire interval like that, and then use the blue as my approximation. So isn't that interesting? That you could just say, let's just, since we know that rectangles are really, it's easy to compute the area of a rectangle. Yeah, why not just form this rectangle, right, over the same interval AB? How do I determine the height? Well, what if I just pick the smallest y value, right? So this would be a very this would be a gross underestimate of the area in red, because it is ignoring all of this right here, right? So that's one way you could do the approximation. Another way you could do the approximation is, yeah, instead of using the absolute min, use the absolute max, which it looks probably around here. So maybe I could use that as the height of my rectangle, and then just make the rectangle again go across the entire interval AB, and then I'll use that dotted green now. So now my stuff is multicolored, looks really messy, but hopefully you get the idea. So I could use that rectangle in green, that green area, as a way of approximating the area in red. Now this would be an overestimate because we're including all of this, right, which is not a part of the red region, right? So you could do that in one way, and just use either a rectangle based on the absolute min or a rectangle based on the absolute max, and then compute the area and use that as our approximation. But you can see it's not a very good approximation. So how can we improve of this? Well, instead of using one rectangle, let's use many rectangles. And how do we accomplish that? Well, instead of having one interval just going from A to B, we're going to split this up into what's called a partition of A and B, where we use many intervals. So this is what it looks like. I am just going to draw a few more hash marks here along my x-axis. And now, so I'm basically introducing a lot more x values. And since I'm having a lot more x values, I am going to relabel my x values. So just having A and B right, isn't enough. And I don't want to use like A, B, C, D, E, because then technically I could run out of labels. So this is what I'm going to do. These are X values, so I am going to label it X, but to indicate that it's a specific X, I'm going to use a subscript. And here I'm going to start my counter from 0. So this will be X0. So the 0th X is my first X value there. Then the next one will be X1. The next two will be X2. And depending on how many I have in here, let me do another one, another specific one. And then I'll have some more in here. I'm just going to call this like the dot, dot, dot. So the pattern will continue until I get to B. And I'm going to relabel B, and I'm going to call it X sub n. Right. So basically what we have here, right, and let me kind of do this off to the side. This right here is called a partition of the interval AB. And the way we're going to do it, and we'll always use it in this form, so partition of the interval AB into n uniform, or n equally spaced intervals, right? So into n equally spaced intervals. So that means that the distance between x1 and x2 is the same as the distance between x2 and x3, right? And that distance, let me kind of label it up here. That distance is the same. We use the same notation that we've been using a lot through differential calculus. We're just going to call that distance delta x. All right. Okay. So, or actually, in fact, yeah, let me go ahead and put the delta x below. I don't want it shouldn't be above there, right? So let me put the delta x right there. Okay, good. So we have our partition. We know how, and in a second we'll figure out how to actually calculate this delta x. It's a pretty easy calculation. Then what we're going to do is for each of these smaller intervals, so relatively speaking, you see how much smaller this distance is as opposed to going all the way directly from A to B. So for each of these now, we're going to use a rectangle, right? So use one rectangle to cover the interval from x0 to x1, and then another rectangle to cover the interval from x1 to x2, and so on until we've covered all the intervals, right? So what will it look like? Well, in my initial example, I showed how you can use like the absolute min and the absolute max to figure out the height of the rectangle. Well, you could certainly do that, and there are other ways you can figure out the height of the rectangle. One way is to, from each interval, use just the left endpoint. So I'll show you a few of those, and then I'll show you what it looks like if you use the right endpoint, and then you can also even use the midpoint, so the middle of the sub interval. Okay, so what I'll do is I will mark each of the x values that I'm using with the red x, so like that. So if I'm using that one, I will, it's like I plug this x value into the function to figure out the height of the rectangle, so it would be right there. And then I would cover the sub-interval with that rectangle, and it looks like that, right? Let me show you again. So for the second interval right here, from x1 to x2, if I use that again, now I would have to go all the way up here, and then go across, and then down. All right. So these two indicate what the rectangles would look like if I use the left endpoint, right? What if I use the right endpoint? So now let's look at this interval. If I were to use the right endpoint, then it would be here. And then I would use this x value, go up to the graph, and then once I hit the graph, I would stop, and then I would go across that subinterval to make the rectangle. Here's another example of a right, using a right endpoint. So using that, go up to the graph, go across, and then that's my rectangle. The third, and there's a third like commonly used one, is the midpoint. So let's say for this interval, if I wanted to use the midpoint, then it would be right in the middle, right here. So I'd have to figure out the number between these two numbers, use that as my x, and then figure out the height of the rectangle, and it would look like this. Now when you use the midpoint, you have to go to the left and to the right and cover that interval. So it's kind of misleading. So technically I shouldn't have, let me see if I can take out this piece now. There we go. Yeah, so I shouldn't see that. It's one rectangle where the height of the rectangle is based on the x value that's in the middle of this interval. It's quite the mouthful. So let me show you again another midpoint. So this would be the middle of the next interval. So I'm just gonna draw an imaginary line here so I don't have to erase it. It will go up to the graph of the function, and then from that y value go a little to the left, little to the right, and then cover the interval, right? And then you continue that pattern dot 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 until you get to B, right? So once you have a rectangle that covers this last subinterval, then you've created, or you found the last rectangle. So let's say that last one is also a midpoint, just so you can see it again. The midpoint of this interval, it would be roughly right there. So I would have to go up. This would be the height of the rectangle, and then that would essentially represent the width of the rectangle. And there we go. All right. And then what we would do is, I'll just quickly color these rectangles, and we would find the area of each of these rectangles, add them all up, and that would give me the approximation of the area that's under this curve between x equals a and x equals b, right? So that's essentially what a Riemann sum is. Now let's introduce some notation that will allow us to kind of describe this in a symbolic way, right? You remember, in math we want to be able to take these ideas, right? That right now we're looking at a picture that hopefully is very clear, even though it might be a little messy, but we kind of get what the picture is saying. Let's translate that into a symbol, all right? Okay, and we'll kind of do this in stages. So remember, what we're trying to do is approximate the area. Well, what we would do is we would have to take the area of these rectangles, right, and then add them up. So let's kind of figure out what the area of the rectangles would be. And remember, in order to figure out the area of the rectangle, we have to choose a specific x. So we would have to choose an x value. So we need a symbol for that, right? We need a symbol to indicate what x value is being chosen. So this is a symbol that is consistent with several books and resources. Now, because of the number of intervals, I am going to use x sub k, right? So the k will essentially tell me if I am picking the x from the first interval, the second interval, the third, all the way up to the nth interval. But since I'm already labeling the endpoints as like x1, x2, x3, I can't use the same x1, x2, x3, so I have to do something different with this. And there are two things that are often done. One is to put a bar above it, right? To just say this is the special x that we're going to choose from each of our subintervals. Or sometimes you put a little asterisk there, right? So this represents the x value chosen from the kth, it's kind of a funny word, the kth subinterval. All right, so it's basically, is it the left? For us, anyway, it will be, is it the left, is it the right, or is it the midpoint? And questions will tell you that. Questions that are going to ask you to compute this sum will tell you which of the three methods to use, right? So that's our x value. So now let's figure out what happens. So again, what we do, we're going to take each, remember what we did, we would take each of these x values, and then we would have to figure out the height of the rectangle, right? The height of the rectangle. Well, how do we do that? We plug it into the equation for the function. So we evaluate f of x at this special x value, right? So it will look, so for the first subinterval, it looks like this. F of x bar, I'll use the bar 1. That will give me the height here, how tall that rectangle is. But then to find the area, I have to multiply it by its width. But I know the width, right? The width is what I'm using this delta x to represent. So I have to do times delta x. And then that would give me this error right here, the first one. Then I would just redo that process, but now with the different x value. So then I'd have to add to that, because again, we're trying to add up all these areas. Take your function, plug in the second x value, and then multiply it again by the width of the rectangle. And then plus, I'll write down one more specific one, and then I'm going to do the dot dot dot. So you'll have f of x bar 3 times delta x, and then plus dot dot dot. Finally, f of x bar n times delta x. Man, all that for a little area. But again, it looks messier and it looks more complicated than it actually is. Now we still haven't written down a formula for delta x. We'll do that in a second. Before we get to that, if we look closely at this expression, right, it has a lot of terms, right? Because suppose n is really big, you know, like 100 or 1,000. You have a lot of terms, but all those terms have a delta x in common. So I can actually factor out the delta x. So I can write this as f of x bar 1 plus f of x bar 2. And now I'll do the dot 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 plus f of x bar n. And then, so I'm using square brackets there as my delimiters or parentheses, and then times, so factor out that delta x, right? So basically, when you look at this, you know, you're just going to be adding up some function values, and you're going to be multiplying by delta x. Now, let's say, so what is delta x? So where delta x is equal to, well, let's see if we can figure out a formula for delta x. Maybe you want to even kind of pause the video again, create some suspense, and think of how we defined delta x, and then see if you could come up with a formula for it. But let's think it through, right? So you can either pause it and discover it on your own, or if you just want to continue watching, you can do that. Remember what we said, that delta x represent the length or width of all the small subintervals, right? Well, the length of the big interval, well, it would be b minus a, right? So this is the length of the big interval that we started with, b minus a. But then we have to divide that up into how many? N equally spaced subintervals, right? So we need to take this length, this original length, and break it up into n equally spaced subintervals. So I have to divide the b minus a by n, right? And this is one way that it's described, and this is what we call our Riemann sum or Riemann approximation, right? Now, there's one other thing we can do to make this notation a little bit easier to look at, and it's what's in parentheses. Now, I'm going to introduce a notation, and it's something that some of you may have been exposed to before, not necessarily even in a math class, but maybe in a computer science class. But this is a sum, right? And it's a sum with a very nice pattern. If you notice, pretty much everything stays the same except the subscript. It just changes from 1 to 2, and then it goes all the way up to n. So that sum can be represented using what we call sigma, Greek letter, sigma notation, right? And this is a very standard notation in math, that anytime you have a sum that follows a certain pattern that you can observe and then describe symbolically, just use the sigma notation. So what is this? So here's the Greek letter sigma, and it's uppercase sigma. And let's look at the pattern in the sum. There is a function value, there is an x value with a bar on top, which is just telling me that it's a special x value that I'm choosing. But what changes from one term to the next? So all of these things here, like this is a term, this is a term, this is a term. The only thing that changes as you go from term to term is a subscript. So in the sigma notation, you put like you use another letter or variable, or sometimes it's called an index, to indicate the number that is changing as you go from term to term. So we typically use something like k or I or j, right? I will use k, right? So that represents the pattern, and then in the sum I have to indicate where does the k or the index start. Well, it starts with the value of 1, and the way you indicate that is by doing this, k equals 1, and then you have to put it where it ends. So I'll put it right there, right? So this right here alone tells me, it indicates what I have in square brackets right here, right? So let me put that just to indicate this, the similarity, like what indicates what. But then I have that delta right here, right? But so if you notice, the delta, the way we're doing our Riemann approximation, the delta, it doesn't depend on which interval you're using. In other words, delta x here is a constant, right? So we could have and that's why we were able to factor it out here, because it's a common factor or constant factor of all these terms. So what happens is, when we switch to sigma notation, it is preferred to distribute the constant back into the sum, right? So here's the last thing I'm going to write down, right? And all of these are saying the exact same thing. It's just a matter of how how you think about it, how you want to represent it. But also you want to be able to understand the different representations. So you'll have your delta f, your f of x bar k, and then times the delta x, and then you sum all of those up, and that's what's indicated here. So I could have technically just gone from the first expression here and then jumped to this, but I just wanted to do it kind of sequentially so you can see how the notation kind of morphs from one form to the next. And this is what we call, so this is what we define as our Riemann sum or Riemann approximation, right? So I'll just say Riemann sum. And depending on the method that we are using to choose our x bar, it might be the left, the right, or the midpoint Riemann sum, right? So I'll do that and say the three common methods for choosing x bar k are, and they're called right for the right endpoint, so right, or left, or the midpoint or middle. I'll use midpoint, sounds fancier. The midpoint methods, right? So so you can have a right Riemann sum, a left Riemann sum, or a midpoint Riemann sum. So I just wanted to kind of give you a background as to why it's used, the notation for it, and then in a follow-up video we'll do some wonderful examples. So hope to see you in the next video.